In this video, we're going to dive a little bit deeper into something that we've barely touched on as we've gone through this course, but is really important. And that is all around this basis that stress is directional. And we've seen this a little bit in our combined loadings. It matters whether you're in tension or compression, which way your forces are going. But this also really matters if what we're looking at is at a different orientation than how we normally look at it, right? So for example, we've been talking about combined loading and lots of different stresses that can be on something. So let's say, I have a beam here, just as a kind of rough example, and it has some, here's a distributed load. And I don't know, maybe it has some other loading on it type of thing. We've been looking at very specific points when we've been doing these combined loadings, right? So we might take, this little section right here and pulling out a stress element. So that's that little 2D shape where we say, okay, here's my little point that I'm looking at, and it has some, some normal forces on it, and maybe some shear stresses or something on it that looks something like this. I have a shear stress or a normal stresses, the Y direction, X direction, a shear stress, something like that for this little element, this little point that we're looking at. All of these shear stresses, normal stresses on it. But if we take that element and rotate it, so we're looking at that same point, but instead of looking at this square being perfectly in line with the X and Y axes as we think of them, we rotate it. Right, so now we're looking at it at a slightly different angle. And what that does is changes the value of all of those stresses. All of these stresses that we had on there before now have different values, and they could have different directions, different orientations that these shear stresses are pointing now. Right, so if I take this and I turn it, even if I'm looking at the same exact point, but I'm just looking at a little bit of a turned version of it, all of those stress values change. And I know the big question here would be, why would we care? Why would we care at all that when I rotate this, that all the stresses are different? And there's a few different answers. One of them is that maybe we want to orient this point, this little element, a little bit differently. Say you have some, let's say I have some rod here that's welded to, I don't know, another rod. I have some corner. At this corner, I'm meeting at an angle. I wouldn't want to take a stress element here that is perfectly like with the X-Y axis system that I have, right? I'm not really lining up with that weld. I don't know what the stresses are along that weld itself. So I might be interested in, well, is the weld going to fail? I need to know the stresses on the weld itself. So I would want to reorient this element so that instead of being right through it, it would be aligned with that weld, right? So hitting at the same angle of that weld for my little element that I'm pulling out. So I'm kind of going through this little rotation where maybe I know what all of the stresses are if I have this element, but now when I rotate him, say 45 degrees or however much we rotate him, then I don't know what those stresses are now, and I need to find out what those stresses are. This can also be a way to find out what the maximum normal stress and shear stresses are for any rotation of this element, right? So we can find out those maximums for any given rotation to make sure that we're not going to exceed any maximums that we might have. So we've got two methods of tackling these stress transformations, and in this video we're just going to talk about the equation method, which is pretty straightforward. It's mostly plug and chug into some equations. But first we need to talk about the positive sign convention so that when we put our numbers into these equations, you can get all of the signs right, because that's the biggest place to make a mistake with these transformations, is you really want to make sure that all of your positives and negatives are going in the correct directions. So for these stress transformations, the positive sign convention, not position, positive, the positive sign convention is going to have your normal element here. If your normal stresses are pointing outwards, away from the element, that's the positive convention. So if we think about it in like XY terms, here's the y-axis, here's the x-axis. In the positive x direction and positive y direction, if they're pointing in those directions, then those are positive. Here's normal stress in the x direction, normal stress in the y direction. Now our positive for shear stress is going to be when it makes a clockwise motion on our x face here. So this is our positive shear. This is what a positive convention for shear looks like. So it's pointing upwards, pointing in the y direction on this x face here. It's also on our top face, it's pointing towards the positive x direction on our y face there. Shear stress in the x and y directions here, that is the positive version for these. And this is really helpful when we rotate things. If our signs change, for example, we go to a, negative normal stress, we know that that'll come into compression, right? It'll be pointing towards it instead. And so when we do these transformations, we do a rotation. Essentially what's happening is that we're given some angle theta that we're rotating by. We originally had our y and x, but now our new y and x align with our square, right? So this is x prime and y prime once we rotate it, where we're rotating through some angle theta that we're given. And then we can find these y, normal stress y prime, normal stress x prime, and then the shear stresses, which is tau x prime y prime. So shear stress x prime y prime, to denote that these are different from the one that we saw above. Right, so the primes just mean that this is the changed orientation. This is the rotated orientation. Now that we've moved it from the original xy axes to these xy, or to the x prime y prime axes, these are the changes that they've gone through. This is the new orientation, the new stresses that we're seeing at this rotation. And again, for that angle, counterclockwise is positive, right? So counterclockwise is moving counterclockwise up from the x-axis here. So this angle is coming up out this way, right? Up from the x-axis. Positive is counterclockwise. So for our equation method here, there's really two main equations that we're going to use to find this normal stress x prime and the shear stress x prime y prime, which are going to be based on those original sigma y, sigma x, and tau xy. So for our sigma x prime, our new normal stress in the x direction that we're rotated along, it's going to be the original normal stress in the x and y directions added together over 2, plus the difference between them, so sigma x minus sigma y over 2 times cosine 2 theta, plus the shear stress xy times sine 2 theta, which I know is a big, long equation. It's kind of a pain to deal with. It's not very exciting, but it's pretty much just plug and chug. All of these values in this equation, you're going to be given right on your stress element here. So all you need to do is plug them in and find out your new stress transformation. The equations are really pretty straightforward. The only issues that really come up with these are making sure that your signs are correct. So positive and negative signs can kind of mess people up with these, but otherwise it's pretty much just plug and chug. Our shear stress is going to be negative sigma x minus sigma y over 2. So this negative is out front of this whole term. Times sine of 2 theta plus tau xy, that's my shear stress, cosine 2 theta. So this is it. These are really the only equations that I need in order to transform my element. To find our y prime, it's actually the exact same equation as my x prime. So sigma y prime is going to be the same equation, but use 90 plus theta as your angle. That's the only difference, right? It's offset by 90 degrees. X and y are offset from each other by 90 degrees always. So if we just plug in a 90-degree added angle to our angle that we're transforming by, that'll give us our sigma y prime. Simple as that. We'll go ahead and do a quick example of this. In this example, they've given us a stress element, and these things would usually be determined from your combined loading problems, and then your stress element is just a representation of all of those answers that you got. That state of stress that you found for that, you can put onto this stress element, so that way you can easily see the normal stresses in the x and y directions and the shear stress. So in this, they give us this little stress element, and they say determine the equivalent state of stress if the element is oriented 30 degrees clockwise from the position shown. So we have just a normal xy coordinate system here, and then we're going to rotate it 30 degrees clockwise, which, if you'll remember, our angle is normally counterclockwise is positive. So in this case, if we're rotating 30 degrees clockwise, we're actually rotating by a negative 30 degrees, right? This whole thing is being moved from this x position here down 30 degrees. That's what we're going to be doing, rotating this whole thing down by 30 degrees. So looking at what we're given here, we're given our x normal stress is 80 megapascals, but notice that it's pointing in towards the element, right? So what that tells us, it is a negative 80 megapascals. My normal stress in the y direction, pointing outwards, so it's positive. It is a positive 50 megapascals. And then my shear stress value that I'm given, notice I'm pointing down on this x side, right? I'm pointing down towards this lower right corner, which means that my shear stress is negative. Shear stress is negative 25 megapascals, right? And positive convention says that on the x face, the shear stress points up. So this guy is negative. And then I left all of my equations in here because all we're going to do is pop all of these numbers into our equations, right? We already said we know that theta is a negative 30 degrees. So that's everything we need. Once you pick off everything from this element here and know that your angle is going negative 30 since it's counterclockwise, it's really just plug and chug from there. So let's do some blue. Our new normal stress in the x prime direction, that's this direction that's been rotated down by 30 degrees, right? This is our x prime direction. Our new y prime direction, and we're going to have our element rotated. I'll draw that in at the end so we have a visual. This is just going to be our x plus our y, so that's our x is negative 80, so negative 80 plus 50 over 2 plus, again, x minus y, so negative 80 minus 50 over 2 times cosine of 2 times theta, and theta is negative 30, plus Shear stress, again, shear stress is negative. Very important that we make sure we put this in negative even though our equation up here has a plus sign. Negative 25 times sine of 2 times negative 30, so negative 60. And then all we have to do is punch all of that into our calculator so that we get a new normal stress in the x direction is negative 25.85 megapascals. And we'll do the same with our shear. Tau x prime y prime equals negative, our x is negative 80 minus 50 all over 2 times sine of negative 60 plus, again, negative shear stress, negative 25 cosine of 2 times theta, so negative 60. Gives us a shear stress, tau x prime y prime. If I plug that in the calculator, of negative 68.8 megapascals. Again, if I want the y prime, all I need to do is do my x prime equation again. Just make sure that we're adding 90 degrees to this. So for my y prime, instead of using this angle of negative 30, I'm going to use an angle of 60, right? That would be negative 30 plus 90 would give me 60 degrees. So I'm putting in theta as 60, but using the exact same equation. So negative 80 plus 50 over 2 plus negative 80 minus 50 over 2 cosine 2 theta, so 2 times 60, is our y value of theta, plus negative 25 sine, and then we know 2 times 60 is 120, so I'm just going to write 120 there. Pop it all in the calculator, and we get negative 4.15 megapascals. Notice that this actually changed, right? Before, our sigma in the y direction was a positive 50, and now it is a negative 4, right? Negative 4.15 megapascals. So changing that orientation completely changed the sign, completely changed the magnitude, made a very, very different stress situation on our element. So what that would look like is that since this guy was rotated down 30, so he's down here now. We originally had our x and y, and now that's been rotated. Y prime, x prime, where this angle that we've gone through, now we've gone down by our angle theta, that was negative 30. We moved clockwise, we moved down by 30 degrees. And our new elements on here are going to be our y is negative 4.15. That looks like this, going inwards, 4.15 megapascals. Our x is also negative, going inwards, 25.85 megapascals. And then that's mirrored on both sides. And then our shear stress, again negative, which means it points down on the x side towards that corner, and then back away, so that way my shear arrows always meet up. And this value was, what was it, 68.8 megapascals. So this would be our new state of stress, right? Our element rotated looks like this and has these new values, these different values from when we rotated it, right? That rotation caused all of these values to change. So this is our stress element at 30 degrees clockwise. So along with doing these stress transformations, one of the other reasons we might want to do them is because we want to know what the maximums are. For any rotation of that element, what is the absolute maximum? What is the angle that gives us the highest normal stress and the highest shear stress values? And so the way we define those is with a couple of more equations. So our maximum normal stresses for any stress transformation, these stress elements, we call them principal stresses. These principal stresses are just the maximum normal stresses. So max normal stress. And we can find the angle at which we're getting a maximum normal stress, right? Whatever rotation is giving us that maximum normal stress, that principal stress, is given by tangent of 2 times the angle of the principal stress is the original shear stress over the normal stress in the x direction minus the normal stress in the y direction over 2. So this is all in my denominator, and my shear stress is in the top there. So this is how I can find the angle of those principal stresses if that's what I'm interested in. Or if I want to find the principal stress, we'll call them sigma 1 and sigma 2. Those are going to be our principal stresses. I can find sigma 1 and sigma 2 using my normal stress in x direction plus normal stress in y direction over 2 plus or minus the square root of sigma x minus sigma y over 2 squared plus the shear stress squared. Right, so this plus or minus here, this square root, since a square root can give us a plus or a minus answer, that's what gives us 2 different values for the principal stresses, right? So sigma 1 and sigma 2, one is in the new x direction, one is in the new y direction, but it's unclear which is which, so we just say sigma 1 and sigma 2, they're going to be our maximums 90 degrees from each other. Where something that's really helpful to clock about this equation is that this portion of the equation is actually the average. Right, all you're doing is adding 2 things together and dividing by 2. That gives you the average normal stress. And this whole equation gives us the maximums. So at principal stresses, I'm going to star this because this is important. At our principal stresses, your normal stress is maximized. And the shear stress is 0. There is no shear stress. Right, so there's no sigma x prime y prime does not exist. No shear stress at the principal stresses. But what if we wanted to find that max shear stress? Right, we've got a couple more equations for that max shear stress. We can find the angle for the max shear stress using tangent of 2 times sigma sub s, right? So that's for our angle for our shear stress, is going to be negative sigma x minus sigma y over 2, all over the shear stress. So very similar to our principal stresses, just kind of inverted and made negative. And then our max shear stress value, tau max, is given by plus or minus the square root of that whole end of the equation that we had before. Right, so sigma x minus sigma y over 2 squared plus shear stress xy squared. Right, it's just the second half of our principal stress equation, but completely removes the sigma average portion. So sigma average is not included, but at this max shear stress, the normal stress will be the average. Normal stress is average normal stress. So while this portion of the shear stress max equation is going on, our normal stress at this time is going to be the average, which is again sigma x plus sigma y divided by 2. Just those two added together by 2, that gives us our average average normal stress. So for principal stresses, there's no shear stress, but at max shear stress, there is average normal stress, which can be a little bit confusing. But if you remember those two things, it'll help you out tremendously. So let's look at another quick example, finding all of these maximums that we can now find. So in this example, we're given a stress element here, and it asks us to represent this state of stress in terms of its principal stresses, as well as finding the maximum shear stress and the associated normal stress. So again, it's going to be a lot of just plugging and chugging, right? We're just going to be popping things into the equation and seeing what it spits out. The key with these, again, making sure you have all of your signs correct. So in our little element here, we have in our x direction, sigma x is going to be negative 20 megapascals, right? Because he's pushing inwards in the negative x direction. Sigma y is in the positive y direction, so that'll be a positive 90 megapascals. And then my shear stress, is in the positive direction this time. It's pointing up on this x side here. So that is 60 megapascals. So to find my principal stresses, we'll start there. My principal stresses are just going to be this equation up here, this wide equation that I've ripped from the page before. So our sigma for both 1 and 2 are given by this equation. So I'm just going to start popping my numbers in there. Sigma x is negative 20 plus sigma y is 90 over 2. Plus or minus square root of negative 20 minus 90 over 2 squared plus that shear stress of 60 squared gives me, in my first part, it gives me 35, and then plus or minus my square root gives 81.4 when I plug those things into the calculator. All right, so this is how I end up with my two different stresses. So one I add, one I subtract. So for the first one, I'll just arbitrarily call it sigma 1. I add those together and I get 116 megapascals. And then if I subtract them to get sigma 2, I will get negative 46.4 megapascals. Now, those are the principal stresses, and that's really all it asked for. But if I wanted to draw the picture for this, I would need the angles, right? We typically want to know what angle these are occurring at. And my equation for those angles, as we talked about on the last page, was tangent of 2 times theta p is that shear stress over sigma x minus sigma y over 2. If I rearrange this, I get, that my theta, theta p, is going to be inverse tangent of, what's that shear stress? 60 over x is negative 20 minus 90 over 2, all over 2, dividing this out, gives me an angle of negative 23.7 degrees. Negative 23.7 degrees. So if I were to draw out this new shape, right? My rotated element here. This negative 23.7 degrees tells me that I'm rotating clockwise down, right? I'm rotating negative. Here's my original X and Y. Here I've rotated down to X prime and Y prime. My maximum normal stress here occurs when this angle is 23.7 degrees. It's rotated down from our X clockwise at 23.7 degrees. And if I want to know, my other angle for my principal stress, I could just add 90, right? That would give me where this Y location is. So I have the angle for my principal stress, where that's hitting on this guy, but I don't know which one sigma 1 is and which one sigma 2 is. I don't know which one is X and which one is Y. But we had that handy dandy equation back at the beginning of the video where we said, where was it? It's a really long equation. It's a really long, annoying equation that's hard to remember, which is why we have another method, not just an equation method. We also have a graphical method. We'll do that in the next video, though. To figure out which one is which it goes on our Y prime and which goes on our X prime, we can use that sigma X prime is sigma X plus sigma Y. And those are our original sigma values. So negative 20 plus 90 over 2 plus sigma X minus sigma Y over 2 times cosine of 2 theta. And now theta is that theta p, right? So 2 times negative 23.7 plus the shear stress is 60 sine 2 theta. So sine 2 times negative 23.7. And when I punch all of that into my calculator, I actually find out that this value is negative 46.4. Oh, look, it's my sigma 2 value. Right? This matches my sigma 2 value exactly. So if I wanted to draw this in, I could say, okay, this guy, well, I drew him immediately the wrong way. So he's negative, so he points inwards, right? He points in towards the element. This principal stress is going to be 46.4. That's our maximum stress in the X direction that we can have. And then for our Y here, it's positive, so it points out 116 megapascals. And then we can go through the same process of just plugging things in for our shear stress. Right? So for our shear stress, what do we have? Tmax is just the second half, of our principal stress equation, right? It's just this half of the principal stress equation. So we actually already have this number. We already calculated it. We don't need to plug everything in again because it's sitting right here, right? Our max shear stress is 81.4 megapascals. Now I'm not going to add him onto this element here because if you'll remember, at our principal stresses, there is no shear stress. So our max shear stress is sitting at a different angle, a different orientation than our max principal stresses. And actually that angle is always a 45-degree difference. The difference between those angles is always 45 degrees. But for the second scenario, our shear stress is this 81.4, and the associated normal stress, we also already calculated. This first term is the normal stress. So this is our average. This term is our max shear stress. So we have this guy. Sigma average is 35 megapascals, and we can draw the stress element associated with him if we wanted to. But these would be our answers, right? We have our average 35 megapascals, max shear stress 81.4 megapascals, and then we also found these principal stresses and found out which direction they were going in. So it's pretty much as simple as that. Again, just plugging and chugging through the equations. It's relatively straightforward, if not a little bit difficult to understand the rotation of everything and why we do it, but it's mostly just plugging things in and solving that way. In the next video, we'll talk about a graphical method, which some people like more, some people like less, in terms of understanding all of this and how it all works together.